All right, so welcome to the deep dive. You're here because you really want to cut through all the clutter and get right to the good stuff in AI research. And today we're going to be really dissecting this this new model called DiffRhythm, and it's out of Northwestern Polytechnical University and CUHK Shenzhen. And the big thing is full song generation. We're talking 4 minutes and 45 seconds.
Wow.
Vocals and accompaniment. And they're doing this in 10 seconds.
Really?
Driven by just lyrics, like a style prompt. And the architecture is surprisingly simple and clean. And thankfully, they made the code open source.
Nice.
So the big idea here is that DiffRhythm is the first latent diffusion model that can do this full song creation end to end.
Okay.
And with this kind of speed and simplicity, it's a big deal. It totally bypasses all the stuff that we've seen before, generating separate tracks or using these multi-stage models and just the slowness of language model inference. So yeah, if you're really into the cutting edge of AI music, then this is a deep dive you don't want to miss.
I think what's really interesting about DiffRhythm, especially for people who are deep in AI music research, is that it's going for this full song generation in one go.
Yeah.
And it's using this diffusion framework. I mean, we've seen a lot of impressive work out there, but a lot of it focuses on specific parts of a song or uses these really complicated pipelines.
Yeah.
But DiffRhythm goes for this end-to-end approach and uses latent diffusion.
Right.
And that's promising because it could be more unified and efficient way to do things.
Absolutely. And you're probably drowning in AI papers all the time.
Yeah.
And keeping up with all the advancements in music generation especially is tough.
It is.
So this deep dive is like a cheat sheet to help you quickly get what's important about DiffRhythm. We'll cover the big innovations, the architecture, how they trained it, and how well it performs.
Right.
And we're basing all this on their paper, DiffRhythm. Blazingly fast and embarrassingly simple end-to-end full-length song generation with latent diffusion.
Catchy title.
Yeah, right. So let's just jump right into it. What makes DiffRhythm so different from everything that came before it?
So the paper is really upfront about how new and simple this is.
Okay.
And they're not kidding when they say embarrassingly simple.
All right.
They really wanted to make the process as streamlined as possible and get rid of all that messy data prep and those multi-stage architectures that we've seen so much of.
Yeah.
And when you use it, you literally just give it the lyrics and a style prompt, and that's it.
Wow.
It's really different.
And for those of us who actually want to use this stuff, it's huge that it's non-autoregressive, right?
Oh, yeah, definitely.
Unlike those models that build the output piece by piece,
Right.
DiffRhythm can generate so much more in parallel.
Exactly.
Which is why it's so crazy fast.
Yeah.
Plus it's open source, so everyone can play around with the code and the pre-trained models.
Yeah. That's so important for research.
It is. It lets people actually try to reproduce their results and experiment with a model.
And build on it.
And build on it, exactly.
So if we take a step back and look at the big picture of AI music generation, there have been some roadblocks along the way.
Okay.
A lot of the models out there, like Melodist and Melody LM, they just focus on making either the vocals or the instrumental track.
Yeah.
And they do a good job at that.
They do.
But anyone who's ever made music knows that the vocals and the accompaniment have to work together.
Right. You need that interplay between them.
Exactly. It's what makes a song feel whole.
Yeah. Imagine trying to enjoy a song by just listening to the isolated vocals.
Oh, yeah. Or only the instruments.
Right. You lose the whole vibe.
Totally.
So then you have these commercial platforms like Seed Music and Suno 2.
Right.
They can generate the combined audio, which is cool.
Yeah. And the results are pretty impressive.
They are.
But the problem is they don't tell us how they do it.
Yeah. It's like a secret.
Yeah. No open source no detailed papers. So as researchers, we can't really dig into their methods or build on their work.
Right, it's a black box. We see what comes out, but we don't know what's happening inside.
Exactly.
Then there are these academic projects like Song Creator and Song Editor.
Yeah.
And they're at least trying to generate the vocals and accompaniment together.
Yeah.
Which is good.
Definitely a step in the right direction.
But they often rely on these super complicated multi-stage architectures.
Right.
And that can make it really hard to actually design and train the model.
Yeah. And to make sure it's stable and can handle a full-length song.
Yeah, the more complex the system, the more likely it is to break down, especially when you're trying to make longer and more intricate pieces of music.
Absolutely.
And then, of course, there's the whole approach of using large language models.
Right.
LLMs are great at understanding these long-range dependencies, and they can generate pretty coherent musical structures, but they're autoregressive, which means they generate the output one step at a time, and that can be really slow.
Yeah, that latency can be a real deal breaker if you want to do real-time stuff or make interactive music tools.
Yeah, or even if you just want to experiment quickly in research.
Exactly.
So DiffRhythm is trying to solve all of these problems.
It is.
So how does it actually do this end-to-end generation so efficiently? Let's dive into the architecture.
Okay.
The paper describes a two-stage process.
Right.
First, they use a variational autoencoder, or VAE, and then they use a diffusion transformer, or DIT.
Okay.
Let's start with the VAE. What does it do in this whole setup?
So the VAE is super important because it does dimensionality reduction.
Okay.
It's basically like learning this compressed but information-rich representation of the raw audio waveform.
Right.
Because raw audio signals, especially for full songs, are these super long sequences.
Right.
And that can be a nightmare for diffusion models computationally.
Yeah.
So the VAE's encoder takes this massive waveform and squeezes it down into a much shorter sequence in a lower dimensional space.
Oh.
But it tries to keep all the important details of the original audio.
Right.
And then the decoder takes that compact representation and tries to reconstruct the original song.
Okay.
They managed to achieve a compression factor of 2048, which they call F.
Wow.
And they work with a 64-dimensional latent vector at a frame rate of 21.5 hertzes.
Okay.
The main takeaway here is that this compression makes the diffusion process way more manageable.
So it's kind of like taking a huge high-resolution audio file and turning it into a smaller, more efficient format without losing the important audio information.
Yeah, that's a good way to put it. The architecture they use for the VAE is based on Stable Audio 2, which is already pretty well known for its audio compression and reconstruction abilities.
Right.
And it's a fully convolutional network, which works well for audio of different lengths.
Got it.
So you feed in the raw stereo audio waveform, and the encoder maps it to that latent representation.
Interesting. How do they train the VAE to do both the compression and the reconstruction so well?
Well, they use this really clever loss function during training.
Okay.
It's not just comparing the raw reconstructed waveform to the original.
Okay.
They use a multi-resolution short-time Fourier transform loss, or STFT loss,
Okay.
which basically compares the frequencies at different scales.
Got it.
And this is perceptually weighted and calculated separately for the mid-side and left-right stereo channels. So they can preserve the spatial audio information better.
Interesting.
And then on top of that, they also use adversarial training with a convolutional discriminator network.
Oh, yeah?
And they actually made this discriminator way bigger, like 4 times more parameters than the original stable audio version.
Wow.
Which makes it even better at telling the difference between real and reconstructed audio, especially when it comes to those fine, high-frequency details.
So it's like the discriminator is this super picky critic pushing the VAE to make those latent representations as realistic and detailed as possible.
Exactly. But here's the really cool part. They do this lossy to lossless reconstruction thing.
Lossy to lossless.
Yeah, so they train the VAE only on high-quality lossless FLAC audio.
Okay.
But during training, they randomly throw in some MP3 compression just to mess with it. But the target is still the original lossless audio. They even randomly change the MP3 variable bitrate quality using this library called pedalboard.
Okay.
So it's like simulating different levels of compression.
Gotcha.
And by doing this, they're basically forcing the VAE to learn how to deal with those nasty artifacts that MP3 compression creates.
Right, because MP3 is lossy. It throws away some of the data.
Exactly. And the VAE has to figure out how to get those high frequencies back.
That's pretty clever. It's like training an image algorithm on blurry pictures so it can learn to sharpen them.
Yeah, exactly. And there's one more trick they use called latent truncation.
Latent truncation, okay.
This is during the training of the diffusion model. They basically take a random chunk of the VAE's latent representation from a longer song, and they use a fixed length portion of it to train the DIT. And at the same time, they grab another short random segment from the same encoding and use that as the style prompt.
So it's like they're showing the DIT different parts of a song to help it learn different style.
Yeah, that's a good way to think about it. It probably helps with consistency during training too.
That makes sense.
Yeah.
Okay, so we've got the VAE creating this compact, latent representation of the audio.
Right.
Now let's talk about the diffusion transformer, the DIT. How does it use this latent space to actually generate the song?
So the DIT works entirely within that latent space that the VAE created. And its job is to generate the latent representation of a whole song.
Right.
It starts with random noise, and then it goes through these steps of denoising, refining it over and over again, guided by the lyrics and the style prompt.
Okay.
Diffusion transformers have gotten really good at making high-quality stuff in other areas, like images and even text-to-speech.
Right.
And the way they do it is by learning to reverse this process of adding noise. So it makes sense to apply this to audio because music has all these long-term dependencies that you need to capture.
Yeah, it's not just about individual notes, it's about the whole structure and flow of the song.
Exactly.
So how do they actually incorporate the lyrics and the style into the DIT?
Well, the DIT is conditioned on three main inputs.
Okay.
The style prompt, a time step embedding, and the lyrics.
All right.
So the style prompt, which is that short segment of the VAE's latent representation, it goes through this long short-term memory network, first in LSTM.
Okay.
And the last hidden state from the LSTM basically becomes this global embedding that captures the style of that audio clip.
So it's like extracting a stylistic fingerprint from that little snippet of audio.
Yeah, exactly. And then you have the time step embedding, which is pretty standard in diffusion models.
Right.
It tells the DIT where it is in the denoising process.
Gotcha.
And then there are the lyrics. They're converted into a sequence of phonemes using grapheme to phone conversion, or G2P.
Okay.
And then those phonemes are embedded into vectors.
So the phone embeddings provide the actual linguistic content for the vocals.
Right.
And then all three of these, the style embed, the time step embedding, and the phone embeddings, they're all combined and fed into the DIT at every layer.
Exactly.
So they're using techniques from sequence modeling and NLP to guide the audio generation.
Yeah, and for the DIT's architecture itself, they went with a really interesting and efficient choice.
Okay.
They decided to use stacks of Llama decoder layers.
Llama, the language model.
Yep.
Interesting.
Which is pretty smart because Llama is super popular in NLP, and there are all these optimized implementations out there.
Right.
Like Unsloth and Liger kernel, which can speed up both training and inference a lot.
Yeah, I've heard of those.
They use techniques like kernel fusion to make things faster.
And that directly contributes to those super fast inference times that we were talking about.
Exactly.
So they're basically taking advantage of all the advancements in NLP to make their audio generation model better.
Yeah, reusing these existing efficient architectures and techniques is a really smart move.
Totally. What about the training of the DIT itself? What kind of loss function are they using?
Well, they're using this thing called the conditional flow matching paradigm.
Conditional flow matching.
Yeah, it sounds complicated, but basically the model learns to estimate this velocity field that guides the transformation from a noisy latent distribution to the actual data distribution of the song latents.
Okay.
And it does this through a defined ordinary differential equation, or ODE.
Gotcha.
So during training, the model is trying to minimize the difference between the velocity field it predicts and the actual velocity field you need to get from that noisy latent state to the clean latent state at any given time step.
Right.
And it does this all while taking into account the lyrics and the style.
Okay.
For sampling the time steps during training, they use a logit normal distribution.
Huh.
Which is cool because it lets them adjust the weighting of different parts of the diffusion process.
So they can make the model focus on refining the audio generation where it matters most.
Exactly.
Okay.
And then when they want to actually generate a new song, they start with random noise in the latent space and use this thing called a deterministic Euler ODE solver.
Okay.
They only need a small number of steps, just 32, and they use a classifier-free guidance scale of 4.
Right.
And this efficiently generates the final latent representation of the song,
Gotcha.
which is then decoded by the VAE to produce the full audio waveform.
So we've got the VAE for handling the audio representation and the DIT for generating in the latent space using the lyrics and style. But the paper really stresses that this lyrics to latent alignment mechanism is super important for getting clear vocals.
It is.
Why is it so difficult to align the lyrics with the vocals in song generation, especially compared to something like text-to-speech?
Well, song generation is way more complicated than regular text-to-speech.
Okay.
Because you're not just trying to synthesize speech, you're trying to create vocals that fit within a whole musical arrangement. So, first of all, you have these gaps in the vocals. There are often long instrumental sections where there's no singing at all.
Yeah, that's true.
So you can't just rely on the typical alignment methods that are used in TTS, which assume a continuous stream of speech.
It's more sporadic.
Yeah. And then there's the accompaniment itself.
Right?
You can sing the same lyrics over completely different music.
Right.
So it's tough for the model to figure out the exact relationship between the lyrics and the audio because the musical context can change so much.
So the model has to figure out not only what sounds to make from the lyrics, but also when to make those sounds in the song, even with all the instruments going on.
Yeah, exactly. And the authors found that the usual text conditioning methods that work in diffusion-based TTS, like cross-attention or just sticking the text embeddings onto the audio features, they just weren't good enough for getting clear vocals in songs.
Okay.
So they came up with this new sentence-level alignment method.
Sentence-level alignment.
And the really cool thing is it only needs the start times of the sentences in the lyrics.
That seems really efficient. So how does it actually work?
So you start with the lyrics, which usually have timestamps for each sentence.
Right.
And then you convert each sentence into a sequence of phonemes using G2P.
Okay.
And then you create this special sequence that's the same length as the VAE's latent representation of the whole song, but it's just filled with padding tokens at first.
All right.
And then for each sentence in the lyrics, you take those phone tokens and you overwrite the corresponding section in that padded sequence.
Okay.
And you figure out where to start overwriting based on the sentence start time and the frame rate of the VAE's latent representation.
So it's like they're creating this sparse sequence of phonemes that's timed with the song, but they're only putting in the phones where they're supposed to be singing.
Exactly. And by doing it this way, they can train the model to specifically learn the connection between those phonemes and the generated audio in those sections.
Right.
And it really improves the clarity of the vocals without having to manually label every single word or phone, which would be a nightmare.
Yeah. It sounds like a really elegant and practical solution to a very tricky problem.
Yeah, they found a good balance.
Okay, so we've covered the architecture and the it's like the lossy to lossless training and the sentence level alignment.
Yeah.
What about their experiments and the results they got with DiffRhythm?
So they trained DiffRhythm on this massive data set of about 1 million songs,
Wow.
which adds up to around 60,000 hours of audio.
It's a lot of data.
Yeah, it was a mix of Chinese English and instrumental music.
Okay.
And they had to do a lot of prep work like cleaning the lyrics and extracting the phonemes and the VAE latent representations,
Right.
which speeds up training a lot.
Makes sense. So how did they evaluate how well the model was doing?
So they did separate evaluations for the VAE and the full song generation.
Okay.
For the VAE, they compared it to Music 2 Latent and the VAE from Stable Audio 2.
All right.
And they used these standard audio metrics like STAY-Y, PESCI, and MCD.
Right.
And they tested it in 2 ways, lossless to lossless, where everything is FLAC audio, and then their special lossy to lossless scenario where they train on FLAC but evaluate on the reconstructed MP3 audio.
Okay.
And the DiffRhythm VAE beat both of the other models in every test.
Really?
Yeah, it had much better STOI and PCE even under lossless conditions.
Yeah.
But the most impressive part was how much better it was at reconstructing audio that had been compressed to MP3.
Right.
The other models really struggled with that.
That's pretty significant because a lot of music out there is in MP3 format.
Exactly. It shows that their VAE is much more robust to those real-world compression artifacts.
It is.
The paper also has some visualizations that show how their VAE does a better job of cleaning up the MP3 artifacts and reconstructing the harmonic content, especially in the frequencies where vocals are.
Okay.
Oh, and they said that their VAE has 157 million parameters.
All right.
So yeah, the evaluation really shows that their VAE design and training strategy is working well.
So their VAE isn't just good at compression, it can actually handle real-world compressed audio and make it sound better.
Exactly.
That's really cool. Now for the full song generation, they compared DiffRhythm to SongLM, which was one of the best text-to-song models before. And they use a mix of objective and subjective measures.
Right.
So they used foam error rate, or PER, to measure how clear the vocals were, and freshet audio distance, or FAD, to measure the overall quality of the audio and how similar it was to real music.
Right.
And they also had people listen to the generated songs and rate them on things like musicality, overall quality, and vocal clarity.
Yeah, those listening tests are important.
They are. And what they found was that DiffRhythm had much better vocal clarity than SongLM.
That's great.
Yeah. And while SongLM scored slightly better on FAD and musicality in some cases, the crazy difference in inference speed for DiffRhythm was a huge advantage.
Yeah, how much faster was it?
Like way faster. Their model had a real-time factor, or RTF, of about 0.03, which means it can make 1 second of audio in just 0.03 seconds.
Wow.
That's like 50 times faster than Song LM.
That's amazing.
It is. It really changes what's possible for real-time and interactive AI music.
It does. Imagine the possibilities.
I know. And they also did this important test where they removed their sentence-level alignment during training.
Oh, yeah. What happened then?
The vocal clarity just tanked. Like it was almost impossible to understand the vocals according to the PER metric.
Wow.
And the overall audio quality was much worse too, even though the basic musical structure was still there.
So that really proves that their alignment technique is essential for getting those clear vocals.
It does. They also pointed out that the PER scores were pretty high overall, which might be partly because of how they were measuring it.
Okay.
They were using mixed audio with both vocals and accompaniment for the automatic speech recognition without separating them first.
Right.
So that could have messed with the results a bit.
Yeah, the background music could interfere with the speech recognition.
Exactly.
Okay.
But even though the objective scores might seem high, the listening tests in that ablation study really show that their alignment method is making a big difference.
Definitely.
So the big takeaway is that DiffRhythm does what it set out to do.
Yeah, it generates these full-length, high-quality songs with both vocals and instrumentals, and it does it really quickly.
And it does it simply.
The latent diffusion framework is clearly very effective for this, and their sentence-level alignment is a big reason why the vocals are so clear.
And the fact that the model is relatively simple means it could be scaled up and optimized even further.
Exactly.
Okay, so for all the AI researchers and engineers out there, what's the big picture significance of DiffRhythm?
So DiffRhythm is a pretty big deal in AI music for a few reasons.
Okay.
First, it's the first publicly available latent diffusion model that can generate a whole song end-to-end with both vocals and accompaniment.
Right.
And that end-to-end approach makes everything so much simpler. You don't have to worry about combining different tracks.
Yeah, it's
all in one go. And second, the architecture and the training method are so efficient that it can generate songs super fast.
and crazy fast.
Which is a big improvement over those slow language model approaches that we've seen before.
Right, and that opens up all these possibilities for real-time applications and interactive tools.
Exactly. And then there's the sentence level alignment, which is a really clever solution to the problem of syncing the lyrics with the vocals.
It is.
And it only needs sentence start times, which makes it really practical.
Yeah, it saves a lot of time and effort. And finally, the fact that it's all open source is amazing for the research community.
Totally.
People can actually dive into the code, see how it works, and build on it.
Which is so important for progress in the field.
It is.
So if you're interested in AI music, DiffRhythm is like a playground for you.
It is. And if you're ready to get your hands dirty, go check out their code and the pre-trained models and start experimenting.
Now, the authors did mention some limitations, which also point to some interesting directions for future research.
Okay, like what?
Well, they haven't really looked into editing specific parts of the generated songs.
Right.
So incorporating techniques like latent masking could be a good next step.
That'd be really cool.
And they're using audio clips as style references right now.
Yeah?
But maybe you could use natural language to describe the style instead.
Oh, that would be awesome.
Yeah, it would give you more control and flexibility.
So DiffRhythm is a big step forward, but it's not the end of the story.
It's more like a starting point for even more amazing advancements in AI music.
I like that.
Now, here's a question for you to think about.
Okay.
What's going to happen to music creation now that we can generate full songs so quickly and easily?
That is a good question.
Think about the possibilities. New tools for musicians, personalized music experiences that are tailored to each listener. And how will human creativity and AI work together in the future of music production?
You know, what new research avenues will open up now that we have this simplicity and efficiency?
Those are the big questions. Anyway, thanks for joining us for this deep dive into DiffRhythm.
Yeah, it's been fun.